On our previous lecture, we have learned magnetic field. We have learned magnetic field, and it is necessary to say that if we change magnetic flux through every closed circuit, in this circuit, electric current occurs. And I think it is necessary to remind. That magnetic flux magnetic flux uh, magnetic flux is equal to surface integral of vector B ds. Now this is magnetic flux. And it is necessary to say that it is important physical value, and because of this there is special units for this. Special units Webers, and 1 Weber is equal to 1 Tesla multiplied by 1 square meter. And as it was said before, if magnetic flux change, induction current will occur. And the question is, what will be the direction of this induction current? And to understand the direction, we can use Lenz rule. Lenz rule. How to read this? Lenz rule. According to this rule, the current induced in a circuit due to a change in magnetic field change in a magnetic field is directed to oppose the change in flux, and to exert a mechanical force which opposes the motion. Exert the to exert a mechanical force, which opposes the motion. Which opposes the motion. So this is Lenz rule. Okay, and how to use this rule? Let's imagine some closed circuit, and there is a magnetic field, that produces magnetic flux through this circuit. Vector of magnetic induction is directed from us to the screen. And the question is, what will be the direction? What will be the direction of induction current in this circuit? There are two possible directions: this and this. And the question is how to define the correct direction. For example, in case when magnetic induction decreases. When magnetic induction decreases, what will be the direction of induction current? And we can answer this question according to the Lenz rule. According to this rule, induction current will try to compensate decreasing in magnetic field. So induction current should produce additional magnetic field to compensate decreasing of external magnetic field. So according to the right hand rule, this direction will be correct, because in this case we have magnetic field with line of magnetic induction that is shown on this picture. So we have the correct direction of induction current if absolute value of vector B decreases in time. Okay, do you have any questions about this? No questions. Okay, so the next step is to connect a change in magnetic flux and induction current, because now, according to Lenz rule, we know only the direction of induction current, but it is also necessary to define a value of this current. And to do this, to define value, let's consider the next system. Let's have a look at a wire that has such form. This we have wire with such form, and on this wire on this wire we have stick, conductive stick that can slipper in left and right directions along this wire. Okay, and let's consider the case. When this stick moves from left to the right, with the velocity equal v. And the system is in homogeneous magnetic field. With induction B. That is directed from us to the screen. And the question is to search some facts about induction current. And as it is possible to see that we have change in magnetic flux. We have change in magnetic flux in this situation because of the motion of this stick. Because of this motion, this area of this closed circuit will change in time. This area will change in time, and it means that magnetic flux will change. But as we know, change in magnetic flux will produce an induction current. And so the question is how to connect induction current with change in magnetic flux. Okay, let's consider that we know this length of the stick. It is equal to some value L. And let's try to define change in magnetic flux during some infinitely small time dt. During this time, the stick will move on some length delta dx. But before this, it is necessary to define the direction of induction current. There are possible two cases, this or this, and it is necessary to choose the correct one. And according to the Lenz rule, the correct direction, induction current with correct direction should oppose motion of the stick. So it should produce force that is direction that has opposite direction to velocity v. So it is necessary to choose the direction that will produce Ampere's force directed from right to the left. amperes force directed from right to the left. And according to the left hand rule, this direction will be correct. I'll remind that according to left hand rule, if we have left hand where vector B is directed to the palm of left hand. So this is vector B, direction of electric current, and direction of amperes force. So in this case, this is a left hand rule. And according to this, we can define, according to the left hand rule and Lenz rule, we may define the correct direction of induction current. So induction current will be directed counterclockwise. Induction current is directed counterclockwise. Okay, and let's try to define change in magnetic flux. As it was said before, that motion of stick will produce will result in change in area. So change in area will be here. This is change in area because of motion of the stick. And let's consider that during some infinitely small time, delta t, stick passed way that is equal to delta, so dx. Dx is equal to v multiplied by dt. And so according to the picture, the change in area ds is equal to L dx. And this is equal to L v dt. But to define magnetic flux, we need not only ds, we need vector ds. We need vector value ds. How to define this? It may be done according to the right hand rule. If we use right hand rule according to the direction of induction current, the sum of right hand will show us the direction of vector ds. And so according to this, the direction of vector ds will be from screen to the us, from screen to us. ds. ds is directed from screen to us, from screen to us, and this means that according to the picture, as we can see, vector b is directed in opposite direction to ds. And this means that scalar product is equal to absolute value of vector b, multiplied by absolute value of vector ds, multiplied by cosine 180 degrees. 180 degrees. 180 because of this. And so we have that it is equal to minus b ds. Minus b ds. Minus b d in ds. And this means that according to this formula, the change of magnetic flux is equal to b ds, and this will be minus b ds without a vector, and this will be minus b l v d t. And from here we can define that derivative of magnetic flux with respect to time is equal to minus b l v. Okay, do you have any questions about this? No questions. Okay, and let's try to find something that is connected to induction current. The reason of current is always electromotive force. So let's try to define electromotive force in this case. And let's presume that electromotive force is caused by Lorentz force. That occurs as a result of motion of stick with free charges inside it. So let's try to calculate this Lorentz force. Lorentz force that connected with the motion of this stick. We know from our previous lecture that Lorentz force is equal to Q cross product V and B. And according to the picture, that vector V is in the screen and vector B is perpendicular to the screen. So because of this, we can define that vector V is perpendicular to vector B. Is perpendicular to vector B. It's perpendicular. So from this we can make a conclusion that F is equal to absolute value or modulus of vector F, and this is equal to Q multiplied by absolute value of V and B, and this will be equal to Q multiplied by modulus of vector V, modulus of vector B, modulus of vector B, and this multiplied by sinus, and the angle will be 90 degrees. 90 because the directions of vectors V and B are perpendicular, as it was mentioned above. So it will be Q V B, absolute value of Lorentz force. And let's calculate work of this force. Let's calculate work of this force. Calculate work of this force along the stick. Along the stick. This work will be A is equal to linear integral from 0 to L F d r, and this will be according to the picture. We know that electric charge, because of induction current, electric charge will move from down to up, and it means that as we can see, the direction of Lorentz force is here, and vector dr is has the same direction. So vector F has the same direction as displacement vector dr, and this means that F scalar product FDR is equal to absolute value F multiplied by modulus of displacement vector dr, multiplied by cosine 0 degrees. Cosine 0 degrees. And so it will be just absolute values FDR. And so we have that our integral simplifies. It will be just f r. So we have a simple definite integral instead of linear integral. So now we can substitute our value of Lorentz force here, and we will get integral from 0 to L Q V B D R, and it will be just equal to Q V B integral from 0 to L D R, and this will be equal to Q V B L. Okay, and I'll remind that this is work of Lorentz force, and this Lorentz force is the reason of induction current. So this work is equal to B L V multiplied by Q. And we can remember from one of our previous lectures that relation of work and electric charge is equal to electromotive force. So electromotive force of induction in this system is equal to A divided by Q. This is according to one of definitions of electromotive force, and it will be B, L, and V. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, I will just I will clean some things that we don't need anymore, and I will leave just necessary formulas that we have obtained. So as you can see, these two equations has almost the same right sides. And it means that from here we can define that electromotive force of induction is equal to minus derivative of magnetic flux. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, I'll remove this. And it is necessary to say that obtained formula is known as Faraday's law of induction, or simple Faraday's law. This is Faraday's law of induction, and but I think it is necessary to write this law in more general form. So let's consider a circuit that contains n turns. It contains many turns, n turns. All turns are connected in series. All turns are connected in series. And we know that in case of connection in series, electromotive forces add to each other. And it means that in case of n turns, we should add all electromotive forces in all turns. So in this case, we have that electromotive force of induction is equal to minus sum of these changes in electromagnetic fluxes. And as you know from calculus course, we can change places of derivative and sum. So it may be written as d by dt, and the sum of magnetic flux. And this sum of magnetic flux is often called flux linkage. This is a flux linkage. Flux linkage. Flux linkage, this is a value psi that is equal to sum of all magnetic fluxes in all turns. And in case of the same magnetic fluxes in n turns. In case of the same magnetic fluxes in n turns, we will have that psi is equal to n phi b. So in this case, we have this flux linkage. And we can use flux linkage here, and we will obtain that electromotive force of induction. Electromotive force of induction is equal to minus derivative of flux linkage with respect to time. With respect to time. With respect to time. And this formula is known as Faraday's law of induction. Faraday's law of induction, or just simple Faraday's law, or Faraday's law, or Faraday's law. Faraday's law. Or Faraday's law. This formula. Faraday's law of induction. Okay, do you have any questions? No questions. Okay. Okay, so in this case, I will move this formula together. I'll move this formula together, so we have Faraday's law of induction. Okay, and let's return to the case of circuit with one turn. So in this case, if n is equal to 1, in this case, flux linkage just equal to magnetic flux. Just equal to magnetic flux, and it will be equal to S and B ds. BDS. Okay, and the derivative of flux linkage with respect to time, derivative is equal to d and the dt, dt, and here we have surface integral b ds. But I think it is necessary to replace this derivative with partial derivative, because vector b may depend on coordinates. So it is necessary to use partial derivative in this case. So it is necessary to use partial derivative in this case. And we can change places of integral and derivative, and it means that we obtain dB ds ds dt vector, and here we have ds. Here we have ds. Okay, and what about left side? Electromotive force. According to one of definitions, as we can remember from one of our previous lectures, electromotive force is equal to linear integral along closed line of some E V dl, where EV is a non-electrostatic field. And non-electrostatic field. So in this case, we can say that we can rewrite this in simple way as this integral plus 0. Why? Because if we remember electrostatics, we can remember that such integral of electrostatic field intensity as integral function. So in this case, we have that in case of electrostatic field, it will be equal to 0. So we can substitute this here. And we will get this plus this, but without with E instead of V. And so we can rewrite this in some another way. L and E. EV is a non-electrostatic part of electric field, and electrostatic part of electric field. dl and so from here we can write, if we sign this as some electric field intensity, non-electrostatic and electrostatic part of electric field intensity, and we will get linear integral along closed line L E dl. E and dl. Okay, do you have any questions? No questions. So we have obtained that electromotive force of induction may be written as linear integral of electric field intensity. Okay, and this means that it is possible to remove this, and let's substitute our conclusions into Faraday's law of induction. And after substitution, we will get that such linear integral, of electric field intensity is equal to surface integral dB dt and ds. And this sorry, I have forgotten minus before integral, because in this formula we have minus, so here we also need to put minus before surface integral. Okay, do you have any questions about this? No questions. So we can say that we have obtained Maxwell-Faraday equations. Integral form. Is it integral form of Maxwell-Faraday equation. Integral form of Maxwell-Faraday equation. And if we have integral form, we will definitely also have differential form. To obtain this, I think we should use Stokes theorem from calculus. And as you can remember, this linear integral E dl, according to Stokes theorem, this is equal to integral SL, and here we have call operator E and ds. Ой. Okay. E E and ds. Okay, so after substitution this here, we will get differential form. We will get differential form that call operator E is equal to minus dB and dt. So this is differential form. Differential. Oh, I just read incorrect name of integral form. Oh, integral form, not form, not for form. Integral form of Maxwell-Faraday equation. And differential form. Differential form of Maxwell-Faraday equation. Differential form is here. Differential form is here. Okay, do you have any questions? No questions. No questions. Okay, if there are no questions, let's continue. Let's continue. Let's consider the situation. Let's consider the situation when we have some current in closed circuit, and of course, as we know, electric current produces magnetic field, and this magnetic field will produce flux linkage. Will produce flux linkage, and of course we know that flux linkage is defined by magnetic flux, and magnetic flux is proportional. Magnetic flux is proportional to the modulus of magnetic field in the not equal, proportional to B, and this means that psi is proportional to absolute value of B, and according to the Biot-Savart law, we know from magnetism from our previous lecture that dB is equal to mu. In isotropic media, it is equal to mu 0 divided by 4 P I d L dLp multiplied by R and divided by R to the power of 3. R to the power of 3. And because of this, we can make a conclusion that B is proportional to current E. And from here and here, we can make a conclusion that psi, flux linkage, is proportional to electric current is proportional to electric current I, to electric current. And so we can write that according to this, we can write this proportionality as a simple formula. Psi is equal to L E. A simple formula L E, where L is inductance. L is inductance. L is inductance. So we have a connection between flux linkage and electric current. And electric current. And electric current. And from here we can, if we use Faraday's law of induction, we can make a conclusion that if current in a closed circuit changes with time, in this case we will have electromotive force of induction that prevents change of electric current, and this electromotive force is also known as electromotive force of self-induction. Electromotive force of self-induction. So let's write this. Electromotive force of self-induction. Electromotive force of self-induction is equal to minus L d I dt. And dt. Di and dt. Electromotive force of self-induction. Electromotive force of self-induction. And inductance. Inductance is a very important value. Very important value because elements of induction, elements with inductance are often used in electronics and multimedia systems. And one of the most important elements is induction coil or solenoid. Induction coil or solenoid. So let's consider. Let's try to find inductance of solenoid. Inductance of solenoid. A solenoid is some wire that has form of spring, with n turns. So we have n is number of turns. Number of turns. N is number of turns. L is length of solenoid, and in this case, we will consider this on practice tomorrow. We will prove this. So in this case, magnetic field inside turns of solenoid is homogeneous and has absolute value B that is equal to mu 0 n I, where letter n is equal to n divided by L. N divided by L. N divided by L. Okay, and S, let's also consider value S, is the area of the solenoid. The area of solenoid. Okay, I think okay, so it may be it may be any solenoid, so I'll use undefined articles in this case. Undefined articles. Okay, so the question is how to find inductance. How to find inductance of solenoid in this case. To find this, let's calculate magnetic flux first. We will prove on our practice that magnetic field inside solenoid is homogeneous and directed as shown here. But area of each turn is also directed from left to the right in this case. So B in this case B has the same direction as ds. And this means that B ds is equal to absolute value of B multiplied by absolute value of ds multiplied by cosine 0. So it is equal to B ds. B and ds. And it means that phi B is equal to surface integral B and ds, and it will be equal to surface integral B ds without any vectors, and this, if we use our formula that we will prove tomorrow, it is equal to, it is S mu0 and E. And E ds. And all these values in integral function don't depend on ds. So we can rewrite them outside of the integral. Outside of the integral. And so we have just mu0 and es. And let's remember that this n is equal to number of turns divided by length. So in this case we can write mu0 n divided by L I s. So this is magnetic flux in one turn. So according to this, we have phi b is equal to this. Okay, what about flux linkage? Flux linkage in all n turns will be equal to magnetic flux in one turn multiplied by a number of these turns. So psi is equal to n phi b, and this is equal to mu0 n, but n to the power of 2. And this will be equal. We can rewrite this as in next form. And area multiplied by L is equal to volume, the volume inside solenoid. Mu 0 and n divided by L is equal to little letter n, and I but to the power of 2, and I v, volume v. So this is magnetic flux, or flux linkage. And here we can remember that flux linkage is equal to inductance multiplied by current. So it will be L multiplied by I. And it means that from here we will obtain that inductance of solenoid is equal to mu 0 n to the power of 2 v and this is also equal, if we remember that volume V is equal to area multiplied by length. Area multiplied by length, so it will be SL. And if we remember that N is equal to N divided by L, we will also get mu 0 N to the power of 2 S divided by L. And divided by L. Now this is inductance of solenoid. Inductance of solenoid. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, let's remove some formula that we don't need anymore. So our purpose was to obtain inductance of solenoid. Inductance of solenoid. So solenoid or induction coil. Solenoid or induction coil. Solenoid or induction coil. It is here. This is a system that is often used. And one of the interesting properties of one of the important properties of solenoid is that its inductance. Its inductance almost doesn't depend on some external factors, but sometimes this dependence is necessary. For example, in sensor touch screens, inductive sensor touch screens. These touch screens has some elements with inductance inside it, and this inductance of these elements is insensitive to some external factors. For example, if we put our finger on this touch screen, sensors will feel this and will react. Okay, do you have any questions? Okay, if there are no questions, thank you for your attention, and I hope to meet you tomorrow when we will do some exercises.